Okay, hello everybody. I'm going to go ahead and get started here because I want to cover a lot today. So, hi, I'm Zach, and today I'm going to be talking about Metro under the hood. So, I'm going to stall time on this slide so people can get the slide deck if they want to take a look at it on their laptops. I just uploaded it, so it might still be processing. But yeah, who here has used Metro before? All right, great. If you haven't used Metro, a lot of this might go over your head. This is sort of a part two to a previous talk that I gave last year called Navigating Dependency Injection with Metro. This talk is going to be a lot more about what Metro is doing under the hood, compiler internals. It's going to focus on sort of the what and why, and occasionally dip into sort of how as well. 5 more seconds for taking a picture of the link. All right. Those previous talks that you should check out, the top left one here is the one that I gave last year. You should also, if you're interested in compiler plugin infrastructure in general, go watch Brian Norman's talk from Kotlin Conf on that last year. So now let's talk about compilers. So I think it's safe to say that developers can sometimes have a sort of fraught relationship with a compiler. They're very judgy. They're constantly telling you what you did wrong. It can be a humbling experience. But in reality, they're code just like anything else, and they have their own quirks and problems going on behind the scenes. It's always a little messy. So let's recap with the sort of North Star example that we'll keep revisiting throughout this talk. So here we have a simple app graph. It exposes this repository, which itself is constructor injected and depends on an API that we provide. So this should look familiar if you've worked with Metro. Now let's look a little bit at what Metro is generating for all of these bits, starting with what we call factories. So to get the dumps that I'm going to show later on in the compiler, I often use this first-party compiler or Kotlin compiler dev kit that JetBrains publishes. It's an IDE plugin. If you work in compiler plugins, it's great. It makes it super easy. So with factories, first let's look at this repository class. So here, Metro generates a nested factory class. This is just called Metro Factory in all the classes. If you try to add your own nested class called Metro Factory, I don't know what would happen, but it probably wouldn't be good. This implements an interface called Factory. I promise I'll say Factory a lot this talk, I'm sorry. Factory just extends provider. And because compiler plugins can mutate the AST, we just generate it right into the class. And one of Metro's fun features is that it can deal with private signatures, and this is how we do it, because nested declarations can access the private internals of their enclosing class. Factories, in general, have mostly the same structure. They override invoke that it inherited from provider, plus a couple of static creator functions. If it has no dependencies, this is just an object class, and it gets reused everywhere. This create function just creates a new instance of the factory. This is what Metro uses all over in graph generation whenever we need provider instances. And then invoke, when we call it, just calls through to give you a new instance via this aptly named new instance function. And that just calls the original target constructor that we were injecting. But that's not all. We store some other data in here too. Things like qualifiers get propagated. If you have default values, those are also propagated, and we'll actually copy those expressions over. And we also add some other annotations to these as well. So we stick this deprecated hidden annotation. This is a trick that I learned from Kotlin X serialization. So this is not code that users need to see, users being like developers working on your code. So we do this so that they don't show up in the IDE as extra noise. We also, for statization, will generate things like JVM static, JS static onto these functions. And then we also use hidden from Objective-C, because if you've worked in KMP before, you'll find that there's just a bunch of stuff that whenever it tries to go to iOS code, it just doesn't like it very much, so we just tell it to ignore those. Lastly, we have what are called mirror functions. So these are funny little things in Metro to help with incremental compilation, which I'm going to call IC for the rest of the talk. And it may, as of like 2 days ago, go away soon in a good way. They just mirror the original target's information all in one place, and it gives us something that we can link against in downstream compilations. So again, we're copying over qualifiers, et cetera, et cetera. And that covers a basic class factory. It's pretty straightforward. Now let's look at provider factories. So that's this API type here, and they work more or less the same way. They get a nested factory class in the class that they were declared in. The name here is an interpolation of the callable that we had annotated, and notably, you'll see it takes an instance because it's a member function of the interface. This instance is plumbed down with any other parameters, has the same semantics. The new instance function name here is the same as the original provider callable. Doesn't really need to be, just this is what Dagger did, and I just matched that. And then the rest is just the same as what class factories are doing. So we don't always need to define these functions in the graph interface itself. Metro also supports something called binding containers, which are basically like modules in Dagger, and allows them to be sort of separated, composable, and also truly stateless. Metro, in this scenario, records extra metadata about stuff in this class. Specifically, we use an API in Kotlin C to add our own custom metadata to the metadata annotations. I resisted the urge to add a YoDog meme here, but it's basically, it gives you an API hook to say, like, give me a byte array of whatever you want, and we can then read that information back when we're loading externally compiled classes. So in our case, we actually use wire and dump a protobuf of a bunch of stuff that we know about what we generated into that class, and that saves us time whenever we're reading these semantics back later. So finally, we'll stitch all this together and generate the graph implementation class. So this again is nested and just extends the graph interface and implements all of its roots. Roots in Metro are accessors, so things that you are pulling off of the graph, as well as inject functions for things like member injection. If a binding is scoped, so say the repository itself, then they get moved to what we call a provider field, and they're wrapped in double check. So double check is a class lifted from Dagger. It's basically just a thread-safe lazy, capital L, wrapper around a provider. Or if the API in this case is passed to the graph as a lazy type, we can also use double check there in a local way. Graphs can also have inputs via graph factories, which is another way to get these bindings in. In this scenario, that previous code just switches to wrapping it in something that we call an instance factory. There's no double wrapping here, just because instance factory also implements lazy. I should probably clear this up, but next, for binds declarations, we generate some other plumbing code for these. So consider this sort of classic example of an implementation type plus its interface. In the graph, we wrote this before, and with the bound instance, the generated code is actually almost the same. We just point at the alias type. So binds in Metro are purely just aliases. If you're familiar with Dagger, Dagger does allow you to scope them independently, but Metro just treats the origin as a source of truth, and everything else is just a pipe to it. Defining them is simple, and then Metro generates some more hidden stuff in here too, called a binds mirror. So these classes just hold a mirror of the original callable. Again, this allows us to beat things like private declarations and propagate some extra details. It's also a function here, even though the original one was property, because there are certain limitations in the Kotlin compiler when you want to add new declarations on the IR side and still have them be visible to downstream consumers in metadata. Then we have some of our usual annotations in here, like this deprecated hidden. But now I'll introduce a couple new ones. So first one is a Metro concept called comp time only. This is just a marker annotation for ProGuard and R8. Metro's runtime includes rules for those tools that can basically say, hey, anything annotated with this is purely used at compile time, and you should just strip them out. The other one is one called callable metadata, and there's a few properties in here, but the basic gist of this is that it's here for linking information about the original declaration back, and we use this extensively in error reporting. It doesn't appear to participate in IC, so it's safe to kind of put these like hard-coded constants in here, but again, that might be changing, so that mechanism may change in the future. And lastly, because we can modify the IR tree that we got here, we can also go through and implement that original binds property in its original location, and this saves us fake overrides from being generated downstream whenever we have other graph implementations. These annotations also get used in provider factories, so we can do the same type of linking there. A good example of this linking is like if you have a graph that's consuming some binding that was provided somewhere way upstream, you don't have all the source information there, and so we basically bolt that on here and then can create a fake synthetic function so that when you get that error, the IDE still jumps to the original declaration. Next, let's talk about multi-bindings. So consider this simple int set. Under the hood, Metro just generates a getter property for every multi-binding. We always generate these as separate getters just because multi-bindings can get quite big. In simple cases, we'll just use the standard library's build set with a known capacity. Again, we know all this at compile time, which makes it nice and efficient at runtime. And then it implements the int accessor to just call through to that generated property. If we make this a provider of ints, then we use a different API at runtime called a set factory. So this is just a regular builder API. Set factory is an internal API in Metro's runtime that implements provider of set. If we have two different accessors for this int set of different contexts, so say we have the provider of ints and then we also just have a scalar request of it. In this case, Metro keeps track of those two, and I'll get more into that later, but it keeps track of how these types are used, and it will fall through to the lowest common denominator, which in this case is the provider. We always prefer the laziest version first, and then we can always convert that back up to a scalar one. So in that case, with a scalar ints one, we still call through that same provider, we just call invoke on the end. What about elements into set? This is again similar to what we were doing before. For scalar access, we can just generate it inline and call add all with the elements that we got. For providers, again, we use set factory, and there's a separate API for adding a collection provider. And that's sets. So a quick note on multi-bindings before we move on to maps. If you look here, like we have multiple instances of the same type going into the graph. And this is, normally this would be a pretty quick duplicate binding error. So Metro takes a note out of Juice's hat here. I saw it. There he is. Yeah. If you have Juice bugs, he's right there. And it goes through and secretly generates custom multi-binding element qualifier annotations on these. So the binding ID property is just the ID of the multi-binding itself. In this case, like the set int. If it has a qualifier, it'll bake that into this binding ID as well. And then the element ID is just a unique deterministic-ish ID, or sorry, not ish, deterministic ID from each contribution. And so as far as later graph validation is concerned, these are all just independent types, and it doesn't have to worry about them showing up as duplicate bindings. So on to maps. Maps, again, are similar in here. The main difference is that we also have to account for keys, and maps can have provider value types. So simple maps, we just use build map. If we don't unwrap the value, then we'll just generate runtime annotation directly in line here too. Because we know all the keys, we can also do all the duplicate checking at compile time. And if we need a provider of the map, then we use a map factory. The added spin here is that map values can also be providers on their own. So for this, we have two new paths that we can take in CodeGen. Simple cases, we just use build map and then inline those provider instantiations directly. Map provider factory is the runtime API that covers this for us. All these provider factories or set factory, all that is like stuff that Dagger paved the way on a long time ago. Again, this just implements a factory of map providers. And once again, if we have multiple multiple access of different types, then we just use the lowest common denominator. And that's multi-bindings in a nutshell. Next, let's talk about assisted injection. So assisted injection is where we pass a runtime parameter into whatever we're injecting, and we create these with assisted factories. So side note, in Metro, you can have these generated for you, so you don't have to do all the boilerplate for them. Requires IDE support. See the docs, it's there. Back to our class though. So our factory, in this case, still has new instance and invoke, but we need to actually support that runtime parameter going through to them. So it's almost identical to the factories that we're generating for regular constructor injected classes, but we plumb those assisted parameters down through invoke and new instance. It also doesn't implement factory because we already have one. So when Metro implements your factory, it generates an inner implementation class. This again is like a pretty simple, like cut and dry bit of code gen. If your factory extends other types, Metro will resolve the single abstract method that it needs for this. Graph factories also work like this. They're really basic, straightforward impls, a lot of repetitive mechanical tedium, which is a great job for code gen. We expose these factories when we expose these factories on the graph, Metro just intrinsically understands where their impls are and will just generate code that invokes them directly. So we call the factory impl here. We pass it an instance of the assisted classes factory. In this case, it takes its own inputs, the API provider, and that's assisted inject. Two left on here. Next one is aggregation. So these are the Anvil features. If you want to work in a big project, you kind of really need something like this, especially if you're working with like dozens or hundreds of modules. So for example, in this case, let's say API and repository impl are in two different locations. So to ease aggregation, we annotate these with contribution annotations, and this instructs the Metro compiler to find them from our graphs and pull them in. To do that, Metro follows Anvil's pattern of generating what are called hints into a known package, in this case, metro.hints. The file name is something deterministic but ultimately ignored, and the compiler allows us later on when we're generating the graph to query this package and ask it, like, hey, give me all the functions in this package. And then we just put the origin of like our original contributing type as the parameter here. So we basically can breadcrumb ourselves back to where it came from. Once we have all of these, we can go look up their origins and then use them in our graph. We look up these functions by the scope name. So in this case, it's the app scope. Grab their origins, finally use them. Not pictured in here for time, but for that repository impl, we would have also generated what's called a Metro contribution interface, and that's what would have the necessary @binds declaration for that contribution into a set. These aggregations that then get merged in with respect to any replacements or excludes rules that you have set up. This is done in two different places in Metro. So for regular dependency graphs, this is done in FIR, and we want that because if you have, say, like a @contributes2 interface, and you have IDE support enabled, then that will actually show up directly in the IDE, and you can avoid doing, manual casts. For any synthetic graphs, so graph extensions, dynamic graphs, it's all done entirely in IR. Finally, let's talk about graph extensions. So if you're coming from Dagger, this is the same thing, or same concept as subcomponents. So say we only use this repository in this graph extension logged in graph. So to link them, we add an accessor to the extension in the original app graph. And when we implement the app graph, we implement both it and all of its extensions in one class. So the accessor goes here, and the extension impl also goes in here. When the extension implements this repo accessor, its graph generation knows about the bindings that are available in its parent, and then we'll also use them. And we also have a bunch of tracking that I'm not going to get into the weeds to on here for recording how it's using it, so we can still respect that sort of lowest common denominator access that I was describing with multi-bindings. Yeah, and then it'll use it from the parent. If this API was scoped, then it gets hoisted into a provider field in the parent graph, and then we access it that way. If you have multiple hierarchies, so say you have 2, 3, 4 levels of like chained graph extensions, it will chain through the relative parents to get to whatever property it needs to get to. And that's sort of it for graphs. I papered over some stuff here, namely, I'm not going to really talk about member injection in this talk. You shouldn't use it if you can avoid it. But this is, at a high level, what Metro generates. It's super similar to Dagger. It's not trying to reinvent the wheel here. It's so similar, in fact, that whenever you enable interop with Dagger, it can actually just go and reuse Dagger's factories, which makes it a lot easier to introduce into particularly like multi-repo orgs. So now let's talk about some of the fun stuff in the compiler pipeline. So the compiler has several phases. Source files basically go into the front end. It parses it, builds a front end IR, aka FIR. There are some extensions that run here. Then it runs through a process called FIR to IR, which converts FIR to IR. And on the IR side, we can do more transformations, and then they're ultimately lowered into their platform targets. So first, we have FIR. This is where Metro's front-end extensions work. This is also where we have to think about things like IDE support. If you've ever written a custom lint, it's a lot of the same considerations. You write code very defensively here. Let's kind of trace through our example. So first, we go through and generate these class headers. This includes our implementation class, our factories. We have to do this in FIR no matter what, because this is the only way that they're going to be exposed to metadata and downstream compilations. Just about everything else, functions, etc., like we can go and add them in IR and request that they be added to metadata. But for right now, at least, we have to do at least the class header in FIR. Once we have the headers in, there's a separate phase called supertype generation where we'll go through and add supertypes. So in this case, for the factories, we'll add the factory supertype. Companion objects also need to be stubbed in here if they need them. Skipping over status transformation, it does some niche stuff in Metro, but not super relevant to the rest of the talk. Supertype generation for dependency graphs is also where we do contribution merging. So it'll do, again, all of the replaces and excludes logic here, but this is only for dependency graphs, not for graph extensions. That's the first two. Status transformation, skipping past that. Checkers also then run on the final resulting resolved code at the end of this process. These are the things that show up in the IDE for warnings and errors. I'm not really going to go into these because Metro has tons of checkers, but they're not doing anything particularly interesting. They're like a bunch of lint checks. If you want to learn more about writing your own checkers, you should go watch Brian's talk. That covers the front end for us, and now let's look at the back end. So this is kind of where the magic in Metro happens. So this is a Perfetto trace of what is happening in the IR side of things for Metro. If you didn't know, Metro does tracing. This is using Android X Tracing 2.0, which is not Android specific and can be used in the JVM. I don't know if Rahul's in here, but it's there he is. Yeah. So if you have bugs, talk to him. It's great. It gives a lot of visibility into what's going on in the pipeline. This is often really just interesting for me, but if you're curious, it's there. So if you look closely in here, there's sort of three-ish phases. This first one is our sort of core transformers. And then there is contribution caching. And then finally, there's the graph transformation itself. Now, this is a simple graph, so it kind of looks like, I don't know, graph processing and the core transformers are like even. But if you go into a big app, so this was generously sent to me by BandLab and used with their permission. There are like 1,000 modules, I think, in their project. And you'll see that like graph processing absolutely dominates most of the work in here. This is also where all the like deep validation Metro does that other tools don't, and where you get a lot of the value out of doing this compile time stuff. So let's dig into these phases. So first, in core transformers, there's a lot that run in here, but in short, this is kind of fleshing out those classes that we stubbed in FIR. So default binding mirror transformer, this is a newer feature that we lifted from Dagger. It also requires some similar mirror support in here. FIR generates the class, IR comes through later and fills in the bodies, easy peasy. Next is contribution transformations. So this is where we fill in those Metro contribution interfaces for contributing types. We get, again, this class in FIR, and then IR comes in and generates the rest. Here's that binds declaration I was mentioning earlier. It's running off the screen, but you get the gist. We also make a record of this contribution to its given scope while we're processing this for record keeping later whenever we need to generate the actual graph. Skipping contribution hint IR transformation, that's going away after Kotlin 2.321. Next up, we have member injection. Again, FIR comes through, generates a members injector class. IR generates the rest. You see a pattern here. It's just mechanical glue. Injected class transformer. You get the class. You get FIR. IR generates the rest. Assistive factories work the same. Just handles the factory. Binding container transformation handles all the binds and provides, and also like binds-like annotations, so things like multi-binds. If you enable binds optional of interop with Dagger, that all runs in here. It's just more factories, more mirror class stuff. The last two that are in here worth covering are these call expression transformers, meaning they transform expressions in code rather than just purely declarations. This first one is this create graph transformer. So this is what takes all these create graph function calls, and all it does is transform them to invoke the generated graph directly. So if you've used like type of in the standard library, it's kind of the same idea. It gives you a hook to compile against, and then it goes and updates it for you during compile time. As contribution does similar. That's just for this .as contribution API, changes it to a direct call and cast to the main type. And that's it for our core transformers. They all run first to sort of get everything in place, and it's all heavily cached as well whenever we need to start referencing it from graph generation. And to make sure that everything is fleshed out before our graphs get to work. Next, we have contribution caching. This is a pretty tiny part, but it's pretty important if you're doing any aggregation stuff. So we had some transformers previously here that participate in this, and then we also introduced a new graph data type that we call metro graph data that records metadata about all the graphs that we saw during that first pass. It looks a little like this. You'll see some information you'd expect to find with the graph, you know, the declaration, the implementation class, the scopes that are declared by that graph, et cetera, et cetera. This holds all the info we need to generate graphs in the last phase. Graphs can declare scopes, and we use these for contribution lookups. And in this contribution caching phase, we need to know all of the scopes that we're going to generate for later. So we basically go and get all the full set of graphs, including any synthetic graphs that we're going to generate, and then go look up all the contributions for them. So we can go look up their hints, and once that pass is done, we have everything we need. And now we get to graph processing. So let's zoom in a little bit here. This in turn has multiple parts as well. So first part is sort of like preparation and validation of the graph, and the second part is generating the final IR after we've gotten through validation. So in this sort of first construction phase, it too is two parts. First part is building this sort of like in-memory graph node and available bindings, and the second part is the actual validation in this seal call. So when we're building a graph, there's a few steps that we need to walk through. Supertype collection is first, and this is where we just iterate through all the graph supertypes. We collect any binding containers that we see along the way, any accessors, all of that. Next, we process any explicitly declared containers. So these would be any that you declared via the annotation. This also includes any @includes dependencies. And we also need to, at this point, go through and get the transitive closure, because containers can include other containers as well. Next, if we're an extension, we need to merge in contributions. Again, this is graph extensions only, and this is the only part of merging that happens in IR. Like I mentioned before, regular graphs do all this part in FIR. The reason why we have this separate is because if we can, we want to do as much as possible in IR. FIR is very fiddly because, again, you're working potentially in an IDE environment. You know, maybe you don't have a return type. Maybe the user hasn't typed it yet. It's a lot easier to write this stuff in IR. Finally, we go through and process all the member declarations. This is where we aggregate all of the roots, including any that we inherited, accessors, inject functions, etc. And now we build the binding graph itself. So this is a data structure that holds all the bindings available to our graph in memory. Bindings are represented through this sealed IR binding structure, and all of these basically map onto different concepts that you have when writing your dependency graphs. Some of these, you know, they have different attributes. So like some can be scoped, some can't. Some have dependencies, some don't. Some can have extra data, like, you know, other annotations with them. The underlying graph data structure itself, though, just speaks this binding type. More specifically, it speaks a sort of framework agnostic API that all of these low-level types extend. These are the foundational types of Metro's graphing validation. Type key is sort of a basic identifier for any binding, which is just a combination of its type and an optional qualifier annotation. Then we have a wrapper type called contextual type key, and this is used to represent how a binding is used. So for example, if it's wrapped in a provider or lazy, it can also indicate if that declaration has a default value set for it. Dependencies on bindings are represented that way in our binding class. And the binding itself then may also have some stuff like, does it have a scope? It has our dependencies, some other things depending on which subtype of binding it is. Papering over stuff, but you get the idea. And that moves us to graph validation. So we don't automatically add all the bindings to this map in the binding graph, though, because not every binding visible to the graph is used by the graph. So we stick them in a lookup that we can actually just go and pull from. The implementation of this, we actually just toss all of our discovered static bindings in here, and then we just lazily pull from it whenever we're populating the graph. I don't have time in this talk to go into the nitty-gritty of it, but this is also where things like, if you have a graph extension and it wants to see if it has a key available, this may give a parent key, for example. If you're also looking at like a constructor injected class that we look up, this is where it handles that implicitly. First thing we need to do when sealing is we need to populate the graph. So this is just a simple BFS from our roots. For each key, we ask the binding lookup if it has something for it. It may have it declared, or if it's an implicit one like constructor injection or an object class, it can materialize a binding for you. If it's absent, though, we have a missing binding. Now, two things can happen here. So if that dependency, which remember is a contextual type key in this case, reports that it has a default value, then we can report this as an absent value. And we can respect that in code gen later by just omitting that argument whenever we need to create that binding type. This is fine, but if we don't have a default, then we have a missing binding here. Skipping over some code here, but Metro, in and amongst this logic, also keeps a running stack of how we got here, and we save off that stack whenever we have a missing binding to make sure that we have a useful report to show to the user. Since this is BFS, we know that the path that we took to get here is guaranteed to be the shortest. At the end, we collect all the missing bindings, and then we report them all together at the end. After we're done with that, we discard that binding lookup, which if you're working in a code base like Squares is really important for memory reasons. If this includes discarding any declared but unused bindings, and this is why you may know that you can have invalid bindings on the graph as long as they're not used by the graph. If we do have any missing bindings at this point, we are done and can proceed. We'll report them with your sort of usual, missing binding, can't find, and it prints out the type key and then the stack that we did to get there. But now this is a spot that Metro also really shines, because Metro really wants to make error messages actionable for users. And in short, Metro just has a bunch of things that it looks for, and will try to materialize a bunch of like hints or similar bindings, things that it thinks you may have meant to happen there, and try to bounce you in the right direction. But if we get through here, we can continue on to validation. And this is where we get into the real algorithms of what Metro is doing. So internally, this calls through to this Metro sort function, which in turn houses a DI-aware implementation of what's called Tarjan's strongly connected components algorithm. So this is a classic algorithm for DAGs, often found in dependency injection or package managers, things like that. Consider our original example, but with a few extra bits. So we'll add like a home presenter, a logger type, a clock type, and these then form a dependency tree. Tarjan is basically just DFS with some extra bookkeeping. If you go look at the Wikipedia page for this, you get the very like theory-heavy algorithm explanation where they like hate variable names longer than one letter. And so I'm going to try to do a more human version of this. And the bookkeeping that we do is each node keeps it has its own index, and it keeps a value that we call its low link, which is basically the smallest index that we can get to from that node. If index equals the low link whenever we're popping back, which we'll get to, you're considered an SCC root, and we can pop it off and emit it. So let's walk through this. We start with the root, in this case, the home presenter. Index here is 0, its low link is 0, we mark that. And then we go on to its first dependency, the repository. Both increment up to 1. Home presenter is now on the stack. Next is this API. From here, it's index 2, low link 2, and we have nowhere else to go. So now we pop back to the first element where index and low link is 2, which in this case is just the API. So it's a root, we pop it off, we emit it out, and then we're done with it. Now we're back at the repository. We move on to its next dependency, which in this case is the logger. Keep incrementing things. Logger goes on to clock, keep incrementing things. And now we're at the end again, so we start popping back again until we get to index equals low link. The clock's index is equal to its low link, so it's a strongly connected component. We pop it off. Same with logger, same with repository, so on and so forth. And now we've completed the traversal. And the best part here is that these emissions are naturally topologically sorted. And that means that if all of these bindings were, say, scoped and needed to be provider fields, this would be the safe initialization order for all of them. And that's pretty handy. Let's look at one more bit in here, and let's introduce cycle. So maybe your clock wants to do logging or something. This is a problem. The logger's already on the stack. The algorithm continues through here. It updates the low link on the clock to 3. And now we would report a cycle in this case. The logger has other paths, so we start popping back until index equals low link. So when we go to the clock is not meeting that, so then we go back one more, which again gets us back to the logger, because remember we went logger, clock, logger. Now we have both of them, and we pop. Now the logger is also set, has an index and low link equal to each other, so we pop everything that we had popped back to, which is now the logger and the clock. This emits an SEC of 2 of those, and Metro will report this as a dependency cycle. And what's nice is that everything that we got out of that is all the elements in the cycle too, so we just show them in a list with each other. But say the clock has a lazy dependency on logger, and this is actually allowable. Metro's sort tracks these points in what we call a, I'm going to sneeze, a deferred set here. And whenever we emit fields for these in a valid cycle case, then we use a type called delegate factory. It's pretty handy. It's basically like a late init provider, so that we can pass a reference around elsewhere that needs a provider, and then we just set it after everything else is set. And that's it for the sorting side. And we have our topology back here for valid graphs. Metro does a bunch of other extra optimizations under the hood here, some sorting for determinism. We use Android X scatter collections for memory performance. We do some node flattening as well, but that's the gist of it. The return topology looks a little like this with some other stuff. We have all the information that you'd want to know when generating a graph. Breezing through here because we're short on time. But we're done here. And now we get to the end game. There are 3 main steps that happen here. First, we do property collection, then shard collection, and then implementing the graph class's roots. Property collection just looks at those return topologically sorted keys and decides who needs properties. There's a number of conditions that cause a property to be kept. For example, anything that's scoped is a conventional one. Other ones might include like multi-bindings with the getters like we saw before. Unscoped providers that are used multiple times, we'll just cache and reuse those. This logic also determines IDs for switching providers, which I'll touch on at the end. There's lots of logic in here. You can go read it if you want in this binding property collector class. Next up is sharding. So in the event that you have a huge graph with like hundreds of provider fields, that might run into like JVM class size limits, and Metro will then shard them if you're over a certain threshold into nested classes to avoid running into those limits. This, along with things like chunking field initializers across multiple init statements, are sort of the primary automatic ways that Metro staves off sort of extreme graph size limits. Small enough graph is just treated like a single shard. And finally, we go through and implement those accessors. So recall our original graph with the home presenter. If we go through and implement it, first we add provider fields that were reported by our property collector. They're wrapped up in double check because these are scoped. Or if we had a valid cycle, this clock becomes a delegate factory and gets initialized at the end. Moving on, we then implement the home presenter accessor. Home presenter and repository in this example both aren't scoped, so they just get inlined directly in here. If those providers were in shards, then their paths get generated slightly differently. And we rinse and repeat for every accessor in the graph until it's all implemented. This is a trivial graph, but this is how every graph in Metro gets generated. Some final bits and bobs here. Switching providers are a mode to avoid class loading on initialization of the graph. This is basically akin to Dagger's like fast init mode. And what we'll do is we'll take these initializations and move them down to a deferred wrapper provider class that has an ID. Use this if you've measured a need for it. It's not enabled by default. There are some caveats to using this, but it'll fall through to basically a giant switch statement in here. Next up, we've got dynamic graphs. These are a powerful tool for tests that allow you to bring binding containers ad hoc and replace keys in an existing graph. This is a neat thing that we can only do with a compiler plugin that you can't really do in something like KSP or capped, because in a compiler plugin, we have access to function expression bodies, and we can go through and read information about the arguments that you passed in to function calls like this. These are generated as synthetic graphs, similar to how graph extension impls are done. And to do this, we create a graph in the same scope as the caller of that type. So, if you have it called in a function, we'll add it to that file. If it's a function in a class, we'll add it as a nested class in that parent class. The name is interpolated from the graph that you are sort of extending here, plus a hash of the input types. And then we just rewrite that create call to call through to this generated graph. This is all the same infra used in graph extensions. It's a really neat thing that we can do with compiler plugins. The last little bit here is compatibility. This is one of Metro's sort of best capabilities. It supports a large moving window of different Kotlin compiler versions and IDE versions. Who here knows what version of Kotlin Android Studio is running? I have questions for you too. Okay, so there are ways to at runtime check what version of Kotlin you're running in. Android Studio in the latest Quail version reports 2.4.255, which is not a real number, or is not a real version. So we had this compat context interface that if you've ever worked with app compat in sort of past Android days for supporting different versions, it's a similar setup where we have this version agnostic interface with a bunch of different compatibility functions in there. Metro will just talk to these, and then we'll have different implementations of this for different versions of the Kotlin compiler, and we'll load that up at runtime and then use one of those. So that way it kind of falls back gracefully when it needs to on older versions. There's a fun script in here that for trying to figure out what version of Kotlin Android Studio is using that basically involves finding a git tag and then looking that up in the Kotlin repo and then finding the nearest Kotlin dev build to that. It works so far. There's also a ton of other really neat infrastructure for testing all of these in the Metro repo. Recommend checking it out. And some future stuff that I'm thinking about are we could potentially do some parallel processing for validation. What would something like a suspend runtime look like? There's some more stuff that we could do as a compiler plugin inspecting bodies, so maybe we can inline simple bodies when we recognize them. Tons of stuff. I think we've got a minute for questions. I know I'm between you and lunch, so no hard feelings. But don't forget to vote, and thank you for coming.